Inge. Hi and welcome to everybody. I'm grateful to the CPM organizers of giving me a chance to talk about this, even though, as you can see from the title, I'm at least in two aspects in a state of sin. I want to talk to you about graph algorithms rather than string algorithms. And the other thing is that one of the big ideas I want to communicate to you is how to translate entirely combinatorial approaches, so the C in CPM, to algebraic approaches. So I hope you find this useful. We're all experimenting with this setup. Everybody is probably at home. Some of you are still in bed, I guess. So I think I will try to drive the slides while I give the talk. That will slow me down considerably. So this will not be a comprehensive talk at all, but hopefully it will be somewhat easier to follow. So just to make sure that we're all on the same page, the problem I want to talk to you about, or I will focus on, is the k-path problem, which is just to find a sequence of connected vertices with arrows in the right direction in a graph. So for instance, there's a path of length 4, 1, 2, 3, 4, and I think if you stare at this slide slightly more, there's even a path of length 6. Let me switch off the camera because otherwise the only thing you can see is my bald head. So to make, just since it's early in the morning, to make sure that we're all on the same page, the k-path problem is to find distinct, and the important word here is distinct, vertices V1 up to Vk. Each of these is a vertex in the set capital V of vertices in the graph, such that consecutive vertices, so vi plus 1, are in the edge set. This is not here to define the k-path problem for you. This is really just a fixed notation. So the k-path problem is k vertices, not k edges, and the set of vertices is capital V, and the set of edges is capital E. And then the k-path problem is given a directed graph G, determine if G has a k-path. So what is important here is that the vertices are distinct. So this is sometimes called a simple path, but I will just call this a path. And there's an obvious algorithm for this, which is just to start somewhere. There are n choices for that first vertex, and then to look at one of the other vertices that may be connected to it. So this could be as many as n minus 1 candidates for that, and so on. Do that for n minus k plus 1 times. So this gives an algorithm that runs among friends in something like n to the k times. So that is the brute force algorithm for this problem. So on finite graphs, this is a finite problem and has a finite algorithm. Of course, this is not when k is large, such as n half. This is an exponential time algorithm, and it should also be clear that we need to expect something like this, because if k equals n, then this problem is just Hamiltonicity to find a Hamiltonian path of sufficient length in some graph, which is NP hard even for undirected graphs. So we expect the complexity of this problem to be pretty bad, something like exponential in k and n, and we could maybe aim for separating the complexities, not as in the brute force algorithm, which I had at the bottom of this line on the left hand, but we could aim for instance, getting the time to be exponential in k and only polynomial in n. And we will succeed at doing this. None of that is new. This is all very well-known stuff, which I expect you've seen before. Before we go on, let's also just observe that in this definition of what a k-path is, we might as well fix the first vertex because of the following reduction. So here is the original graph that I want to find my k-path in, and I will just add a new vertex S, connect that to, in this direction, every vertex in G. So this new graph, G, I don't know, hat S or something, has the property that if G has a k-path without fixing the starting vertex, then G at S has a k+1 path starting in S. So I just wanted to have all these things out of the way. This is also the test technology. So just Inge, please tell me, am I audible? Do my slides move about? Awesome. Okay. So another thing of folklore which I want to introduce for you is the walk sum. So for this, I briefly need to define a k-walk. K-walk is maybe an even easier concept than a k-path. So these are just k vertices such that they are consecutive, but they are not necessarily distinct. So I allow repeated vertices. Come again? Okay, this was not a question. So with this k-walk defined, otherwise please interrupt me. I think we are. This is a small community, so there's if I do something wrong, just shout out. So now there comes something that is maybe new. Let alpha be any mapping from the vertices. Oh, I promised you that this was actually V, from the vertices and the edges to something. Let me write R. R is just any old ring. So I can add and multiply stuff. Then I will define, that is the only definition that you need to remember, f of G and alpha, which is the so-called walk sum. So that's the sum over all k walks, V1 up to Vk of alpha V1, alpha V1, V2 times all the way up to alpha Vk. So there's a bunch of terms, and each of these terms is a product of all the labels I visited on my walk. So for instance, in the bottom left corner, if k equals 4, there is, for instance, the walk starting in this vertex, which I arbitrarily labeled with 3, that goes 1, 2, 3, 4, but there's also another walk like this one, 1, 2, 3, 4, or even this one, 1, 2, 3, 4. Each of these contributes its own term. So let's take the first one. That would be 3 times 3 times 2 times 1 times 9 times 1. So that's one of the terms in the walk sum. The second walk I pointed out was 3 times 1 times 9 times 1 times 2. My God, 3, 1, 9, 1, 2, 2, 9, I think. And the third term, corresponding to the small directed triangle in the top part of the graph, would be 3, 2, 3, 1, 2, 1, 3, and so on. There may be many more of these. In total, there could be n over k many terms. So this is an exponential sized object, the walk sum. So why does this play a role? The walk sum plays a role because there's a very well-known folklore algorithm for it, which is just based on dynamic programming. And at the danger of insulting all of you, I will just spell it out. So the dynamic programming algorithm for this problem is to define for every R and every vertex V some value, let's call that S for sum maybe, of Rk, which is the sum over all R walks of alpha, oh man, V1, alpha, V1, V2, and so on, defined exactly as the walk sum, but ending in VR. And then
so we can only see part of your slides now.
Yes, because I've zoomed in,
good.
because my handwriting is not good enough.
Wanted to...
Yes. And then from time to other, I will do this and zoom out again. Thank you, Inge. Where VR is this last vertex. And then with this definition, the following dynamic programming expression presents itself. I can compute this value from previous values by multiplying with uv and v, if I did everything right. Right, and in particular, the value I was after, f of g of alpha, the walk sum is now just s of k of, actually I have to sum of all of these guys. So it's going to be something like this. Okay, so this is just dynamic programming. You can also view this as some kind of memory-less breadth-first search. No matter how you view this, then the walk sum can be computed in this time as a matter of folklore, and doesn't do much for us except in the case that I point out down here. If the graph is a directed acyclic graph, such as this one, then we have our first algorithm for k-path, which is just set up alpha to map all the vertices and all the edges to 1, and then compute the walk sum for this labeling, compare it to 0, and if anything survived in this walk sum, then it must have been, because the graph is acyclic, must be a walk that is a path. It can't repeat any vertices because there are no cycles at all in the graph. And each of these walks, which are paths, contribute with exactly the value 1. So I can return, let me use maybe just here for the blackboard, the square bracket Iverson notation. So this just means return 1 if this expression is true, and return 0 or no otherwise. All right. So we are still firmly in folklore territory. And let's see an algorithm for k-path that works not only for directed acyclic graphs, but in general. And the algorithm will be a randomized algorithm. It will be the first one, and we're going to refine this. So the idea would be to let pi be a random permutation of the vertices, and then restrict the edge set to all those edges uv which were in the original graph, but for which pi now satisfies the ordering. So I've done 2 examples down here. So I'm going to throw away every edge that fails to point from a smaller vertex to a larger one in the random permutation. So I guess this guy goes away, and probably some more. I can't see right now. This guy goes away, and this guy goes away. And in the example down here, I think almost everything goes away. So, no, there may be more. Yeah, this one. So with some luck, So the result of this process is guaranteed that the resulting graph V, E prime is a directed acyclic graph. So I can use the algorithm from the previous slide. And that is going to work exactly if the permutation was so friendly as to keep the k-path alive. So here's an example where the original k-path that was in the graph still respects the ordering induced by the permutation, whereas the poor second example graph got all its k-path destroyed.
I'm sorry, why did you need to remove 4, 3?
I may have made a mistake. So which one? 4?
4, 3, the last edge that you removed, it didn't cause a cycle, right?
It did not cause a cycle. That was a mistake. Thank you very much. So I'm not going to switch the colors. So this is still alive. Well, maybe it's even correct now. 3, 7, 7, 2. No, the 7, 2 also has to die. There we go. So now it's correct. Thank you very much. All right. So what is the chance for a false positive? So the algorithm falsely announcing that there is a k-path in the graph, that is 0. That no new paths arrive, but there's a good chance that there's a false negative. So the algorithm falsely claiming that no k-path exists in the graph, even though there was one before I destroyed edges. So, so this happens unless, so here is, there's at least, assume there's at least one k-path in the graph. Here it is. So then I need, let's call arbitrarily these vertices 1, 2 up to k. Then I want this permutation to be smaller than this value of the permutation, and so on. This has to be smaller than that. Is strictly smaller than that. And this is just basic combinatorics. This is 1 minus how many permutations are there? There are n factorial. And so slight trick here. I don't really care what the last vertex n was mapped to, nor do I care what vertex n minus 1 was mapped to. So there are this many choices, and so on. I don't really care about any of the remaining n minus k vertices in the graph. They can be mapped to anything. But the k vertices that now remain, for those I have exactly one choice, namely the choice described up here, that pi1 has to be less than pi2 has to be less than pi k.
Right, but 4 to 3 still died, right? Because it's not about if there's a cycle or not, it's if the ordering is maintained. When we decide which edges to delete. Or did I misunderstand that?
You did not misunderstand. Was I fast talked into removing an edge I shouldn't have removed? Pi u.
All right, now I understand.
Yes,
sorry,
great.
I thought I misunderstood.
Yes.
So she
yeah.
is right.
Yes, 4 is less than 3, which you can see by subtracting them. Yes. Now 4 is larger than 3. I'm sorry. Yes. Now we are on the same page. So let me just finish this construction. This is 1 minus k factorial. This is our first triumph. This is a polynomial time algorithm with a terrible success probability. So I can repeat this a number of times. So if I repeat this k factorial times, then I now have arrived at an algorithm with running time k factorial times the time it took for me to compute the walk sum, which is this, and error probability 1/2. So I have a randomized algorithm with more or less the complexity I wanted. What has happened qualitatively here is that I was able to separate the complexity depending on k into some function of k, and the complexity depending on n is indeed now polynomial in n. So this algorithm, in the terribly misleading slang of parameterized computation, is called a fixed parameter tractable algorithm, an FPT algorithm. Okay. Again, this is still folklore, and now we move from folklore to famous algorithm, namely the color coding algorithm of Alon-Justet-Zwick, which is sort of the logical progression of this. So let me define a new mapping, chi, for chromatic, which maps the vertices to the integers 1, 2, up to k, and it does so at random. Now, these things are called colors just as a matter of tradition. Again, this is somewhat misleading because they are not colors in the school of graph coloring. They are just integer labels. So maybe think of these not as colors, but think of them as integer labels. But I've shown you two of these. However, traditionally they are just confused with colors. So let's stay in that terminology. So at the bottom, I've given you two of these random colorings, and as before, you can see that maybe our original 4-path actually has received different colors, as here, or it may have received not different colors, but paths that are not, walks that are not paths, like this walk of length 4, certainly has received, can't have received 4 different colors. So here's a K walk that has received 4 different colors, and here is one that has not received 4 different colors and which is also not a path. Okay, so famously, this leads us to an algorithm that is on many people's shortlist for favorite algorithm of all times. It's also a dynamic programming algorithm, and let me also spell this out. So define CR, V to be, so R is now a subset of the colors. V, as before, is a vertex, and I want this to be 1 if there exists a path, P, starting as all our paths in V1 and having exactly capital R many vertices, so as many vertices as there are colors in this subset of colors R, such that chi of V of P, so this is just a clever notation for the colors appearing on P, is exactly R, and otherwise I want this value to be 0. Okay, so this is useful for us because G has a K path if and only if this expression is true for some U and all the colors. So this phenomenon is sometimes called a rainbow coloring, or a polychromatic coloring, or a colorful coloring. And our examples here were enough to understand this. So here is a K path with 4 colors on it. So that would satisfy this criterion. And this graph down here has no such K paths. And just to spell this out, this also allows a natural dynamic programming algorithm, which looks a bit like the one we already had for the walk sum. So let's see, it has to end in U, and then it has to use all the colors already in chi except for the color of U, which will be added when we add U. So if you like dynamic programming, this should be completely should be banality for you. And what we win by this compared to the previous slide is that the probability for a false negative is now 1 minus, well, so here's my path. I want it to be colorful. It has length k. So there are k to the k different colorings or labelings of it with the integers. And of these, those that are colorful are exactly the k factorial many permutations. And this is 1 minus e to the minus k. And to sum this all up, just as in the previous slide, I would now have to repeat this algorithm e to the k time to get an error probability of 1/2. So in total, we will have time O of 2k k n plus m. And this makes us slightly happier because the dependence on k is now an exponential function in the narrow sense. It is not k factorial. It is some constant to the k. I promised you that in order to make this a randomized algorithm, I actually need to repeat this thing e to the k times. So for error probability 1/2, this is our running time, and also, by the way, our space consumption, because no, this is false. Space is only 2 to the k. Okay, so far, I'm still trying to be nice to you because nothing here is new. Many of you will have seen this before, and this was just to to lure you in, because now comes something that may be new to many of you, the wedge product. This is new to you unless you know your algebra, or you know your geometry, or you know your quantum mechanics, or even computer graphics. The wedge product I'm showing you now is extremely well-known construction, which appears everywhere in math, but which is not on the short list of stuff that many computer scientists, including me, are familiar with. So this will be a very full slide with new and not completely easy material. So I hope by now you're coffeeed up and maybe even found your way out of bed. So F will be some field, and you will lose nothing by just assuming that the field is the rationals, and K, as before, will be some integer. Now, we all know what a vector space is, but let me remind you anyway, just to set up notation. So there will be a basis of basis vectors, k of them. So these will span this vector space, and a typical element in f of k will be a vector such as y, and vectors can be written as linear combination of basis vectors. So here is one of these. In general, a vector can be written as a1 e1 plus 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 ak ek, and we will sometimes view these as in this column fashion. Okay, and it's a vector space, so if you have two vectors, you can add them, and this is still something in the vector space, and you can also multiply them by a constant, and that is also in the vector space. Okay, this is all well known, and we have some kind of geometric intuition about these things even. So E3 we can view as something that points in a direction. And then my vector y, which I just defined, let's see if I can do this carefully. I promised points something like here. So now let me introduce something that may be new to many of you, the exterior algebra wedge fk. So the symbol in front of the f is a wedge, looks very much like the AND symbol from Boolean algebra. And the elements living in this object are called extensors, and they look funkier. Maybe it's easier if I just tell you what the basis is. So the basis of this thing are also basis vectors, but now I ranges over subsets of the integers. I will call this thing capital K for the rest of the slide talk. So some typical member in Fk, maybe this X here, which is 3 times E of, now there's a set here, 1, 2, and 7E3. You can also have somewhat more harmless members. Y is also a member of an element in the exterior algebra. But it is indexed by singletons. In general, any A in f of k is written as the sum over all I of AI, which is just some number, it's a scalar in the field, times EI, which is this subset indexed combination of basis vectors. And the Y I defined here and the Y I defined up here are in some sense the same. So the original vector space Fk lives inside lambda Fk using the obvious correspondence where I just confuse EI with EI. But in general, lambda Fk is much, much larger. As you can see, the dimension of this thing is 2 to the k rather than k. So currently the exterior algebra is just a richer, just contains elements that contain more numbers than the vector space. The vector space contains k different numbers, and the elements in the exterior algebra contain 2 to the k different numbers. But what the exterior algebra gives to us is that we can equip it with a product, namely the wedge product. And the wedge product, I will define for you in a minute, but let me just tell you the properties first. So the wedge product is associative. And bilinear, so I can do x plus a, y, wedge, z, and it behaves as you want it to behave. So it is x, wedge, z, plus a, y, wedge, z, and symmetrically in the other direction. So both of the equations that you want hold, but so it is not commutative. In fact, it is, however, anti-commutative on vectors. So x wedge y is minus y wedge x, as long as both x and y are vectors. So this is true for x, y, z in lambda Fk, whereas the highlighted expression is true only for vectors. But that is going to be our central property, because in particular, this would mean that x wedge x is minus x wedge x, and from there it follows that x wedge x has to be 0. So it is alternating on vectors. Maybe we should write this down because this is a good term to know. Okay, we're almost there because now I can. I've written down the properties, and now I get to the definition of how this wedge product is defined. Let's define this by example first. I want E. Since the by linearity and associativity, it is enough for me to define the wedge product on basis vectors. So E1 wedge E2 will be this extensor. E2 wedge E1 is going to be minus E1 wedge E2 by the yellow property. And in general, so the full definition is going to be that E I, oh, by the way, E3 wedge E3 is of course just 0. And in general, EI wedge EJ, where I and J are sets, well, two things can happen. Either I and J contain a common element, in which case their wedge product is just 0, or I wedge J is going to be I of I union J, which is now a disjoint union. So otherwise, times -1 to the something. And the something here really doesn't need to concern us much. It's going to be the sign of the permutation that sends I followed by J into sorted order. And this is just, let's just see this as an example. So E1, E3, E5. Let me wedge that with E, I don't know, 4. So by the alternating property, that is going to be E1, E3, E4, wedge E5. I can drop the parentheses because I promised you that the thing is going to be associative. Okay, so this is how you play around with these things. And just to annoy you, what is X wedge X? What is X? What is Y wedge Y? And what is what I want? X wedge Y, I think. X wedge Y. So you have all this information on the slide, and we will take a 3-minute break, which you can either use to fetch some more coffee or get out of bed or actually do this. Okay, so welcome back. Y wedge y is 0 without any computation because y was a vector, and at the top left, at the bottom left part of the slide, I convinced you that on vectors the wedge product just disappears. X wedge x, on the other hand, I got this to 41 E1, 42 E1 wedge E2 wedge E3. I may have made a mistake, but
No, did you change anything
that's
with
where
your? Sorry, did you change anything with your microphone? Because I hear a lot of noise now compared to before. Is it just me?
I also hear.
So now I moved my microphone about a bit and removed one of the cables. Thank you very much. Maybe this is better. So
Not really. Sorry.
and XY I actually also did. So that was E1, E2, E3 times 6 minus 7 E1, E3. So if you had fun using all these algebraic properties, this is more or less what you should have ended up with. The only point for doing, there are two take-home messages. One is that the fact that the wedge product is alternating on vectors does not extend to extensors. So you can easily have two elements in the exterior algebra that, if you multiply them together with the wedge product, give you something that is non-zero. And the other point, which you, if you actually try this, is to see that most of the time these products just disappear, and when they survive, these factors sort of get more and more of these basis vectors glued to them and become longer and longer, but they can't get longer than, in this case, 3 elements, because otherwise there will be a collision and then they will disappear. Okay. So we will represent an extensor, as on the previous slide, in this form of just writing down the coefficients. And then if we multiply an extensor, so an extensor, so this takes space 2 to the k. We want to compute with these things, so let's write this down. So there's 2 to the k space just to write down an extensor, and multiply an extensor by a vector is this thing, which is large and scary. Wedge, something that is much nicer, namely this thing. So that takes time, something like 2 to the k times k operations in the underlying field. So just one more thing which may be useful for intuition: if x1 up to xk are vectors, then consider the map that sends x1 up to xk to the wedge product of x1 up to xk. So if you did the homework on the previous slide, then it should be clear to you that the form here has to be something like some number in front of the largest wedge product you can form, namely E1 wedge E2 up to EK. Because if any larger product would immediately have 2 identical basis vectors and thereby would cancel. So this thing has to look like this. Any sufficiently large product of vectors in the exterior algebra has to have this form. The only question is, what is in this cloud? And the thing in the cloud is actually a super well-known object to us, because so by definition, the mapping that sends the vectors x1 up to xk to the right-hand side is multilinear, it is alternating, and if you plug in the basis vectors, the coefficient will be 1. So this is a good friend, namely the determinant of the k by k matrix formed by viewing x1 up to xk as column vectors. So many well-known objects and constructions from linear algebra appear in this exterior algebra, and it's just a very powerful object, and the wedge product does many useful things for us. The only reason we didn't learn this at school is that in the many generations ago there was a war in linear algebra between Gibbs, who won, which is why we know vector spaces, and Grassmann, who lost, which is why we don't know the exterior algebra as well. Okay, so with this now defined, the whole point that we want to do is define a mapping xi, Greek xi for x tensor, mapping the vertices to this algebra. So that's going to be our labeling or our coding. Now, if this is a walk, then this will extend to walks. Right, so in my example here, for instance, the walk extensor or the walk sum in the exterior algebra is going to be the sum of all walks in this graph. So for instance, x1, wedge x2, wedge x3, wedge x4, and there will be something like x1, wedge x5, wedge x6, wedge x1, and so on. There will be many more terms as in all our walk sums. But what the algebra does for free for us now is that this walk corresponding to this term in the walk sum potentially remains, whereas this walk corresponding to this term in the walk sum vanishes because x1 and x1 as factors in the same expression will cancel each other, and this will just die. So I can spell this out in general. If V is a walk, that is not a path, then the walk extensor of W is just going to vanish. And in particular, the walk sum, defined many slides ago, for any mapping into the exterior algebra, which was defined as the sum over all walks of F, of Xi W is the sum over all paths. And that is huge progress, that the fundamental difference between a walk and a path is now abstracted into an algebraic property of the ring in which I evaluate my expressions. Because computing the walk sum is still a polynomial time task, and the algebra in which I evaluate the walk sum, the ring, by the properties of the wedge product, now makes all the annoying walks, all the self-intersecting paths disappear. So there are still some issues left. The first issue is, of course, that Xi could just map anything, including all the paths, to 0, and then I couldn't count anything or even detect anything. More annoying is actually the fact that you could have the extensor associated with P could be minus the extensor associated with some other path Q, so they could cancel for this completely different reason. And let's take care of both of these issues in a concrete example. And now we finally back to the color coding example, which we know and love. And now I can do color coding exactly as before, but in the exterior algebra. So let's consider the following extensor coding. I'm mapping every vertex to an element in the exterior algebra, and the element I'm mapping it to is sort of the simplest element I can think of. So I want to map these things to the exterior algebra, and I do that by mapping this to a random basis vector. That is the simplest extensor coding we can think of, and I've shown you an example here. And so the extensor for a path is now going to be E of the random basis vector for the first, E of the random basis vector for the second, and so on, E of RK. And this is going to be, well, there are only two possibilities. Either there is a repeating basis vector on this path, in which case this is all 0, or there's a non-repeating basis vector, or they're all distinct, in which case this is going to be the determinant of a matrix of zeros and ones, so it's plus or minus 1. So in particular, using the exactly the same argument as we had before, psi of p equals plus or minus 1, if and only if all the basis vectors are mapped to are distinct, and there are this many chances for this. So this is the exact same argument as color codings, and the colors in the color coding algorithm correspond exactly to random unit vectors in this setting. So you can see, for instance, this path here. It's really happy because it survived. The problem that I already mentioned on the previous slide was that you can have this nasty situation. So look at this path. So by itself, this looks really good because it has been mapped to 4 different unit vectors. The problem is that this other path has also been mapped to 4 different unit vectors, and they exactly have opposite signs viewed as determinants. So they will cancel. So I need to patch this with a single trick, but this is not so bad. So can have chi pi equal to minus chi q, and that's sort of bad news, frowny. But we can patch this because we will just map into a slightly larger object by sending v to not just a random basis vector, but I will send it to a random basis vector padded with a bunch of wedge a bunch of zeros padded with the same basis vector. So now, and this is the core trick, chi bar of p, an entire path, is now going to be E. I'm running out of symbols here. ER10 wedge 0 ER1 wedge ERK0 wedge E0 ERK. So this is a 2K times 2K matrix, or rather the determinant of such a matrix. By reordering this thing, it's going to be the determinant of ER1 here, ER2, ERK, a bunch of zeros. Okay, and the only thing that can have changed here is the sign in front of this determinant. So by alternation, I can always move the ordering around. So it's -1 to the something, I don't really care, of the determinant. And this thing is, as you know, the square of both of these determinants. So that is the determinant squared of E1 EK. And that's certainly not -1. So no cancellations can happen. Okay, so to sum up the argument, I can choose chi bar mapping the vertex set to random basis vectors padded with zeros in the proper way. And then I just compute the walk sum of G using this labeling. Okay, so this was the simplest extensor coding I know. We code these with so-called lifted random basis vectors. But as soon as you start thinking about this, a whole new world opens up, and you can code with much funkier objects. For instance, you could code with van der Monde vectors. So they look like this. And then if you do that, then the walk extensor of a path will be a van der Monde matrix, which has the properties you want. In particular, it's going to be non-zero exactly if all the vectors are different. So by plugging in those values for our coding, you get an algorithm that is way faster than the color coding algorithm, simply because we have more exciting elements in our coding than just random basis vectors. You can also encode the edges and thereby recover a different famous algorithm for the k-path problem due to Kutis and Williams, based on polynomial identity testing. So to sum this up, what I wanted to convince you of, with both a pedestrian introduction to the wedge product and then the claim that this idea of coding the vertices as elements in this exterior algebra gives us a unified and generalized view that recovers several well-known k-path algorithms and also discovers a few new ones. So to summarize these, the first one was where and I did that in some detail, where I mapped VIs to random basis vectors. That was just exactly identical to color coding of Alun-Justet-Zwick. If I map the VIs to van der Monde vectors, as in line 2 here, then if you now carefully analyze this, that gives you a deterministic algorithm for the k-path problem in time 4 to the k. This is nowhere near optimal. There are much, much faster algorithms than today due to currently Merav Zahavi has the record, so that's 2.5 something. But still, this is very clean and seems to be a good way of seeing that you can map edges to random integers. We will cover the algebraic fingerprinting method of Kutis and Williams. A contribution that is in our paper is that if we map the VIs to random Bernoulli vectors, so the entries are plus ones and minus ones, then we get an algorithm that is able to count the k-paths in this time. And that is actually a new algorithm with a better running time than what was known before. So that is one of the things where this framework not only has some explanatory value in that it generalizes and unifies previous approaches, it also does something that we couldn't do before. And there are many other tricks in k-path that you can express in this framework. It just, to me, it feels very right. It feels as if this is the right way of viewing these algorithms. So I tried to do a bit of advertisement for this wedge product, but embarrassingly, it turns out, and the wedge product, as I mentioned, is super well known in large parts of math and algebra and quantum mechanics. It turns out that we're not really sure how quickly you can compute the wedge product of an extensor with an extensor. So if both sides of the product belong to the full algebra, rather than as we used y being just a vector, then it is not clear to me what the correct complexity of this is. So it's known that you can do this in an expression that involves matrix multiplication, but it seems to be, I'm both embarrassed and slightly annoyed by the fact that this super well-known object does not have an algorithm that we all agree is the best algorithm. Okay, so this was a summary and a single open question to talk about over a beer. Thank you very much for your attention.